Okay, let's start again. So after all these long calculations, as a relief today I will do at least the first half of the lecture in terms of pictures. So it will not be quite as technical as it has been until that. But in the second half of the lecture I will then get back to chalk and talk. But I brought you a few pictures of things we discussed last week. So here's one of the diagrams I've shown you last time, just written with my hand on the board. Here's something really produced with Mathematica. So this is a decay of the period, capital T, of a binary system. For this formula holds for a circular system. Yeah? We also calculated the more general case, but then we specified to the circular case. And for the circular case, we had this comparatively simple formula. And the change of the period, the rate at which the period decays, is given by this factor 1 to the 1 minus t over tsp to the power minus 5/8. tsp is the so-called in-spiral time, the time at which the two mass points in this simple mathematical setting have come together. Yeah? And then, of course, the calculation stops. So you see that in this setting there's a singularity at t equal tsp. So the system starts. Maybe I should take this as a substitute for a pointer. So it starts at a certain time. Then if tsp is very large, then actually it stays constant, almost constant for a very long time. And then it goes down. And asymptotically it approaches t spiral. So this is the formula which we then want to compare with observations. That's something which you can compare with observation. And I've also calculated last time the signal which arrives with the observer at a certain distance. Here we have, in the plane, we have this binary system, the circular binary system. And for simplicity, we assume that we observe directly from the top. Yeah, so it's the best position. And then we get a signal h of t, which is periodic with period 2 omega. But this omega is slowly varying with time. Yeah, it becomes slowly increasing in the course of time. And the amplitude goes with omega t squared. And the omega t, as I said, is time dependent. It has a similar time dependence as, omega is the inverse of the period, so there's there's small wonder that it has a similar dependence on time. So in this case, the power is minus 3/8. And if you plot this function h of t, that's a signal which would really arrive at the observer. You see that it is more or less harmonic over a long time. If tsp is big, then for a long time you wouldn't see any deviation from a pure sinusoidal oscillation. But then it increases. And actually, again, in this simplified setting, it goes to infinity. Yeah, omega goes to infinity, which means that the amplitude goes to infinity because it goes with omega t squared. And the frequency goes to infinity. This means the ups and downs come closer and closer together. And that's what one calls a chirp signal. That's a typical shape of a chirp signal. So the amplitude goes up and the frequency goes up. So it's something like constants over a long time, and then it goes up. Yeah, that's a typical chirp signal. And I said already last time that, of course, we do not expect a real gravitational wave signal to behave in this way over the whole period, over the whole interval of time, which is shown here. But for the in-spiral phase, it's actually a very good mathematical model. In the end, something else will happen. So if we have two merging black holes, then of course the two horizons will come together and the two things will merge, and then there will be something which is called a ring down, yeah, instead of the singularity. Or if it's two stars, we could speculate that, for instance, also a white dwarf and a neutron star, for instance, could form a binary. Then if they come close together, the white dwarf would be considerably deformed. Yeah? A white dwarf is something the size of the Earth. So this is considerably less compact than a neutron star. So we expect strong deformations at a certain instant of time. And then other effects play a dominant role, which were not calculated into our calculations. And even for neutron stars, at some point, the size of the thing plays a role, comes much later than for white dwarfs, but at some stage, the size of the thing and the spins also will play a role, and then we will see considerable derivations from this simple point model. Okay, these were two pictures which last time I've just sketched on the board in a very superficial way, but these things are really produced with Mathematica, so they show you how it looks in a proper way. And now we want to compare this with observation. So now comes the short section, which are entitled Indirect Evidence for Gravitational Waves from Binary Pulsars. So these things, which we have calculated in the preceding 2 or 2.5 lectures, they have been brought into contact with observations, and this was with the help of binary pulsars. To understand this, first of all, I think I should remind you what a pulsar is, then we can speak about binary pulsars. So pulsars were discovered in 1966, and for this discovery, Anthony Hewish got the Nobel Prize in 1974. So this is Anthony Hewish, and this is the instrument with which the first pulsars were detected. It's not the beautiful dish in the back, yeah? That's in Cambridge. So that's the radio dish in Cambridge. This has nothing to do with pulsars. Pulsars were discovered with these things, which looked like junk. Yeah? This iron rod, connected with wires. And that's the way how low frequency radio telescopes still look today. Yeah, if you have ever seen one of these radio stations which are supposed to observe radio waves at low frequency, you will be highly disappointed. Has anybody seen a low-far station? So, yeah, Pavel has seen it. Probably you were disappointed. Yeah. So this is LOFAR is a system of arrays. There are many of them distributed over the Netherlands and over Germany. And they look like that, yeah? Just iron poles coming out of the earth and connected with wires. So if I visited the LOFAR station in Effelsberg you have this beautiful big telescope, movable, 100-meter in diameter. You are highly impressed. And then you turn around and they tell you this is our LOFAR station. And you are tempted to ask, I thought this is your junkyard, yeah? So it looks so disappointing. It's just iron rods and no impressive view whatsoever. But these things can do marvelous observations. And all the technology, all the complicated thing is in the data analysis. In the way in which this enormous amount of data which comes in from these LOFAR stations is evaluated. This requires the most sophisticated types of computers, and this is very expensive, actually. So you wouldn't believe if you see these things that this is something which is connected with a lot of money, but it is actually because of this data analysis. So, okay, we now go back to the year 1967, and Anthony Hewish, together with the students, he built this telescope with his hands. They hammered these things together. And the actual detection of a pulsar was made not by Hewish, it was made by one of his students, Jocelyn Bell. She is now Jocelyn Bell Burnell after she married. So she was a PhD student of Hewish at this time. So she, together with, I don't know, 4 or 5 other PhD students, they really built this telescope. And then they found something interesting. I'll tell you in a minute what they found. And this was published in Nature in '68. And it was one of the most exciting moments in astronomy, I would say. Okay, I'm not old enough to remember myself what happened in '60. I was a schoolboy at this time. But I talked to many people who actually are old enough to remember this time, and they all told this was the most exciting moment in astronomy they ever saw. So what did Jocelyn Bell detect? This is the original. First of all, what was she looking for? She was looking for quasars. So the whole group wanted to analyze quasars. Quasars had been discovered in 1963 by Martin Schmidt, Dutch astronomer. And after a while it became clear, or more or less clear, what quasars are. They are radio sources which look point-like. That's why they're called quasars, quasi-stellar radio sources. So they look like stars in the telescope, but they are not stars. Actually, they are nuclei of galaxies. Because they are far away. They have a high redshift. So this indicates that they are far away. And the very fact that we can see them nonetheless means that there must be very highly energetic processes associated with them. And we now believe that quasars are black holes which are surrounded by accreted matter, and this matter produces a radiation. So they are black holes at the center of galaxies, that's what we now believe, and the radiation, of course, doesn't come out of the black hole, it comes from the matter, which moves around the black hole. Okay, so this was, in the mid-60s, was a hot topic in radio astronomy, so everybody wanted to investigate what quasars are, and this group in Cambridge was one of the groups who did this. But they found something completely different. Well, during their search, it was quite common that they had signals which they called interferences, or Jocelyn Bell used to call it scruff on the signal. Yeah, just some irregular signal which obviously was dirt, which perturbed the real measurement. And they were quite used to this. Usually it came from cars or other metal objects in the neighborhood. So after a while it went away. Yeah, when the car was gone, then of course the signal had gone away. But at this day, 6th of August 1967, when Jocelyn Bell analyzed this measurement, she found something which did not go away. It was this signal here. And it stayed, and it turned with the sky. Yeah. So when this, well, actually it's the Earth which is moving, but it gives us the impression that the sky is moving. This signal was fixed with respect to the stars. So this was a clear indication. This was not a car which was going by, it was something in the sky, some distant radio source. And she talked to her supervisor, Anthony Hewish, and he suggested to look more closely at this signal. So they tuned their telescope, if you want to call it this way, in a different way, so that it could operate at a different frequency and with a higher resolution. This took a while. And then in November, the instrument was ready to take a closer look at the signal, and that's what they got. It's the red line there. That is the signal. Here's a time scale. Here's 0. Here's 10 seconds. Here's 20 seconds. And you see that the signal has regular pulses. Yeah, the shape of the pulse is not at all regular. You see, some of them come down fairly deeply. Others are flatter. So the shape is different, but the position in time of the signal is highly accurate. Yeah, if you look at the minima more closely, the minima of this signal, you find that they are always separated by 1.33 seconds, with an extremely high accuracy. And well, when the group members in Cambridge looked at the signal, they were really confused. Who or what could produce such a signal, which comes with such accuracy, where the frequency is constant to such a high degree? And they seriously considered the possibility that the signal comes from an extraterrestrial civilization. Yeah? So that somebody is, some other civilization wants to send to us a certain message with this signal. And they called this object which produced this message, they called it LGM1. And LGM stands, believe it or not, it stands for Little Green Man. Yeah? LGM1, this was the first name of this signal. And they discovered for quite some time if and how they should publish this. Yeah? Because they remembered H.G. Wells in the 1930s or 1940s, where this fake radio show, yeah, where Orson Welles produced a radio show after the novel by H.G. Wells on an invasion from Mars, right? And many people believed this. They didn't realize that it was just a show, and. So the group in Cambridge was really seriously discussing, should we publish this, in which way should we publish this? But then in the end they did publish it, and of course they didn't write anything about Little Green Man in the scientific publication. It was this publication here in Nature. So it very soberly is called Observation of a Rapidly Pulsating Radio Source. And they made some first suggestion what this object could be. And the first idea which Hewish had, actually, here you see pulsating. It was really the idea that it is something which is pulsating. Yeah, become bigger, smaller, bigger, smaller, bigger, smaller. And the first candidate they investigated was a white dwarf. So they thought it could be a white dwarf which is very rapidly, with a period of 1.33 seconds oscillating. But then they found the thing wouldn't survive this. Yeah, it couldn't oscillate at such a rapid frequency. And the And then, of course, immediately, a big discussion started. What could this be? I said already, this was a big moment in astronomy and astrophysics. So everybody jumped on these observations, and more or less everybody realized that it was something important. But in the beginning, it was absolutely not clear what was the right explanation.
Was it called LGM in the paper?
No. Then they started with calling these things pulsars. Yeah, okay. Pulsating radio source. A pulsar was a short word for this. Was invented by Anthony Hewish, and very quickly this word caught on. So from then on, they were called pulsars. And the official names of all these things begin with PSR, which stands for pulsar, not with LGM.
So it was just a name within their group.
Yes. But you see, if you look at the data sheets from their observations, so you see really LGM written. Okay, so the person who found the solution was Thomas Gold, Austrian-born astrophysicist. Maybe some of you know this name. He is he did a lot of important things. Maybe what he is best known for is a steady-state theory of cosmology. Together with Hermann Bondi, also an Austrian, and Fred Hoyle, an Englishman, he invented the so-called steady-state theory for cosmology. It was a theory that we are living in an expanding universe, but that the density doesn't become smaller in the course of time because matter is constantly created. Yeah? So then the density would stay constant, although the thing is expanding. Of course, we have problems with the standard conservation laws, as you can imagine, so they were willing to modify these standard conservation laws. And this steady-state theory was hotly discussed in the 1950s and early 60s. It was a very serious contester to the Big Bang theory. Yeah? I'm not sure if really the majority of cosmologists at this time, in the late 50s, say, were in favor of the Big Bang theory or of the steady-state theory. But then the cosmic background radiation was discovered, and this was a clear evidence that the Big Bang theory is the right theory. And then from then onwards, only the three inventors of steady-state theory believed in the steady-state theory. Yeah? So they kept on until their deaths. They died, all of them died between 2000 and 2005, I think. And to the very end, they advocated in favor of the steady-state theory. So it's the same person, Thomas Gold, or Tommy Gold, as he was later called. So just the same as Bondi, he had to emigrate from Austria during the Nazi years. So he spent almost all his life partly in England, partly in the United States. And in 1968, he came up with, so it was the same year where the pulsar discovery was announced. I think the announcement was early in the year, January or February, and this was at the end of the year. So, and he managed to publish this in Nature. This is not obvious that he managed to do this. There was a big conference soon after the pulsars were discovered, and Gold wanted to present this explanation, and this paper was rejected. He was not allowed to give this talk. The chairman of the workshop told to him, Tommy, I'm sorry, but if I allow you to speak, then I have to allow every crackpot to speak. So I cannot reject anything. So I'm very sorry, but I have to reject this paper. The idea is too ludicrous. But the Nature editors were obviously obviously not so skeptical about this. So the paper was accepted. And a year later or so, more or less everybody believed that the explanation by Gold was a correct explanation. And what was the explanation? It's not something pulsating. It's something rotating. Yeah, so the name pulsar is misleading, but it had stuck by this time already. And the thing which rotates is a neutron star. Neutron stars had been suggested as hypothetical objects in 1932 by Bade and Zwicky, a famous paper by Walter Bade and Fritz Zwicky. So they were hypothetical. There were no indications that they existed in nature, but it was a theoretical result that a star at the end of his lifetime could end up in what they called a neutron star. That's an object which is not bigger than about 20 kilometers, between 10 and 20 kilometers, but it has the mass of a star, so maybe between 1 and 2 solar masses. So it's incredibly dense. And what Gold suggested was that such a thing could be associated with a magnetic field, and that the magnetic field axis need not coincide with the rotation axis. So the thing rotates about this axis, but the magnetic field is pointing in this axis. Now if there are charged particles around, then they would follow the magnetic field lines. So there would be radiation going out, mainly in the direction of the magnetic field axis. Yeah, like a lighthouse. So a cone of radiation would go out in the direction of the magnetic axis. But as the thing rotates about the spin axis, then this cone would rotate, like a lighthouse, yeah? Like the signal from a lighthouse. And if you are situated at a point where this cone meets you from time to time, once in a revolution. Yeah, of course, you are not running around the star, so you will not follow this cone. It will hit you, then it will go around, then it will hit you again, then it will go around, and so on. And this produces, according to this explanation, yeah, these signals. Yeah, so it's a radiation cone of a rotating neutron star, which meets you periodically, with a period of the revolution of the with the spin of this object. So as I said, neutron stars were purely hypothetical at this time. So there were theoretical studies that things like that could exist, but nobody had ever found any indication in the sky that something like that exists. But here it was. This was a possibility to observe neutron stars in the sky. And as I said, after a very short period, actually, this was generally accepted. One should also mention Franco Pacini. He had published just a few months before the discovery of the pulsars a paper on neutron stars, and he had suggested that they could emit radio waves in this way here. But this paper was before the discovery of pulsars. So obviously he did not bring his idea into connection with pulsars. So I think it's fair to credit Thomas Gold. So I said there was a Nobel Prize awarded for this discovery, and it was awarded to Jewish alone. Jewish got it together with Martin Weil, but Martin Weil got it for some other things. He was the inventor of aperture synthesis, this idea of linking radio telescopes together to get a high resolution. So the only person who was awarded the Nobel Prize for pulsars was Anthony Jewish. Many people say that's a little bit unfair. The person who actually, there's no doubt that he deserved the Nobel Prize. Everybody was agree with that. But that he got it alone. This is, not everybody was agree with that. So the first person who many people think should have also awarded the Nobel Prize was the person who found the signal, yeah, Jocelyn Bell. But she did not get it. Well, she can talk about this quite funnily now. So she did it. She took it lightly. Yeah? She feels no grudge. So she's a very entertaining. I've never seen her live at a conference or so, but I've saw speeches from her on the internet and read speeches from her. So she's a very good humor. So she absolutely feels no grudge about this fact. And also one could argue that Gold would have deserved the Nobel Prize. Actually, I think just discovering something by accident, it's just luck. Yeah? Okay, if you are ready to give the Nobel Prize for that, why should you not also give the Nobel Prize for the person who explained this, yeah, who did really the intellectual work of explaining this? So I think Gold would also have deserved the Nobel Prize, but he never got it. Okay, soon after the discovery of, actually the group in Cambridge found this pulsar which I've shown you, where I've shown you the signals, was the first one, and then very quickly they found more. And also other groups found some. So in the year 1972 and 73, one knew 14 pulsars. And the position of these 14 pulsars were, here, these are the positions of these 14 pulsars. Here's the position of the Earth. They were engraved into this famous plaque on board of the spacecraft Pioneer 10 and Pioneer 11. Pioneer 10 and Pioneer 11 were launched in 72, 73. They went out to Jupiter and to Saturn. They produced these marvelous pictures from Jupiter and Saturn. I'm old enough to remember this. Yeah? I remember very well when these spacecraft arrived at Jupiter and at Saturn and produced these marvelous pictures. And they had this plaque on board, which was supposed to give hypothetical extraterrestrial civilizations who will ever found this spacecraft an idea about men on Earth. So these spacecraft passed by Jupiter and passed by Saturn, and then they left the solar system. They are now outside of the solar system. We do not have any contact with the spacecraft anymore, but they are traveling on, and maybe somebody will intercept them at some time. Then he will find this plaque, and the idea is they get an idea how we look. They get an idea where we are situated in the solar system, and if we know what pulsars are, then probably we have some kind of civilization. So we know a little bit about the universe. That was the idea behind this plaque. Of course, it's very doubtful if we will ever get any response from somebody who found this plaque. But the remarkable thing is that the people who produced this thought that the existence of pulsars and knowledge about the position of pulsars would be a particularly clear indication of that we know something about science, about our universe, and so on. Okay, so much for pulsars. What have pulsars to do? What have pulsars to do with gravitational waves? Well, pulsars by themselves have nothing to do with gravitational waves, but there was a close relationship to gravitational waves when a binary pulsar was discovered. We usually say binary pulsar. The word is a bit misleading. Binary pulsar does not mean that we have two pulsars which form a binary. Binary pulsar means that we have a binary where at least one partner is a pulsar. Yeah? So, and such an object was found in 1974 by these two gentlemen. And again, it was awarded the Nobel Prize. It was again a combination of supervisor and PhD student, in this case Joe Taylor and Russell Hulse. But in this case, the Nobel Committee awarded the prize to both of them. So obviously they had a bad conscience about Jocelyn Bell, so they thought this time we will also get a prize to the PhD student. So so they are still alive, and Joe Taylor is still active. He's a very well-known radio astronomer, and I haven't heard much about Russell Hulse actually, what he had done after this discovery. So what exactly did they discover? They discovered a pulsar which is in a binary. So how did they know this? First of all, what was the original plan? What was they doing? They were just searching for pulsars. It was this discovery was made in the course of a search for new pulsars. They used the Arecibo telescope for this. I think you have seen pictures from this. This is, for many years, it was the biggest radio telescope in the world. It's 300 meters in diameter, and it is situated inside a crater in Arecibo in Puerto Rico. Yeah, so this is not movable, of course. Yeah, so this is just the grid is placed inside this crater, inside a kind of sinkhole, and it cannot move. So you would see what does us a favor to move over this this dish, but what's outside of the view, you cannot see it with this telescope. You cannot move it. And as I said, it was the biggest radio telescope for many years. Probably you have seen in the news that the Chinese bought a bigger one last year. I think it was finished last July or last August or so. This is 500 meters, I think, in diameter. And but this was a telescope which was used by Hulse and Taylor, and they were looking for pulsars. And they found one pulsar which was very, very peculiar. So what you usually saw was a signal which came with high regularity. Yeah, so the period, the frequency didn't change at all. The period was very, very stable over long times. And this thing was different. The period changed. The period became longer, reached the maximum, became smaller, shorter, and then the whole thing started again. So it changed periodically. How do we interpret this? So there's a periodic redshift, blue shift, redshift, blue shift. Yeah? So you see a redshift, then a blue shift, then a redshift, then a blue shift. If you interpret this as a Doppler effect, this means the thing goes away from you, then it comes towards you. Goes away from you, comes towards you. Why should the source do this? Yeah? The only explanation is it is in a binary. Yeah? It is in a binary. Then it comes towards you, goes away from you. Comes towards you, goes away from you. And that was the interpretation of this picture. And actually, because you can measure this with fairly high accuracy, well, actually that's difficult. There are many subtleties which have to be taken into account. First of all, the signal from this particular pulsar was very, very weak. So they could produce graphs of this kind only by superimposing many, many observations. Yeah? So from a single observation, they got almost no information. So the signal was very weak. And then also you have to take the motion of the Earth into account, of course. Yeah? The Earth goes around the Sun. This also produces a small Doppler effect. You have to subtract it from this. But if you do all these things, if you then get something in a clear fashion which really comes from this light source, then you can get a lot of information from this graph about the orbital parameters. And well, I should have said this is the name of the thing. PSR stands for pulsar. B stands for the epoch. This was it refers to the coordinate system as it was in 1950. In later years, the coordinates on the sky were adapted to the change of the of the reference sources. So the B stands for the period, and these are the coordinates in the sky: 19 hours 30 minutes right ascension plus 16-degree declination. So it's in the northern sky, the northern half of the sky, and. When they produced these pictures, then the goal was to derive from this the orbital elements. So they realized immediately that with this thing, one could test general relativity. They realized this immediately. One could test this formula for the decrease of energy, which we have calculated in the last lecture. But for that, and if you want to compare this with the data, well, we can read the period directly from the observation. Yeah, the time from here to here. This is something which can be directly observed. The period can be directly observed. Now the question is, does the period decay in the way as the theory suggests? For that, we need to know all the orbital elements. Yeah, we need to know the masses, the semi-major axis, and the eccentricity. And the question is, can we deduce them from this picture? Well, if you assume that you have a binary, goes around, and you observe the redshift. So the redshift is associated with a velocity, with a radial velocity of one of the sources. The other source is dark. We don't see the other source. Yeah, it's dark and dead and silent. No signal from the other object, from the companion. The only way in which we know that it must be there is because we see the redshift in the other source. Yeah? It's the other object. So. The only information we get is the information about the radial velocity of the shining source, of this radio pulsar. And the question is, can one deduce all the orbital elements from this? And the answer is, if we stick within the Newtonian model, which we have used until now, you cannot. You can deduce only certain combinations of the parameters. And this was done in this paper by Hulse and Taylor, where they reported about their discovery and where they gave some of the parameters of the system. So I already said the period can be read directly from the observation, and it came out it's 7.75 hours. Yeah, so this is the time for one revolution. So two stars which orbit around each other in 7 hours. So that's an enormously short period. Yeah, so you can imagine that how fast these things must be. But as I emphasized already, they are still far enough apart from each other so that the distance is big in comparison to the Schwarzschild radii. Yeah? So in this sense, this is not a relativistic system, not a highly relativistic system. But in comparison to ordinary binary stars, it's extremely close and extremely fast. Okay, you also get the epsilon, the eccentricity. Actually, you get it from the ratio between the maximum and the minimum of the diagram. Maybe I type out a few ideas about how you extract these parameters from the observations, but I don't want to do it here on the board because it would take too much time. So you get the epsilon, but you do not get the A, not the M1, not the M2, and not the inclination angle I. The inclination angle I is the angle under which we see the plane of the motion. Yeah? So we get only combinations of them. We can only extract combinations of them from the from the observation of redshift. And yeah, for this combination, this is a semi-major axis. This is the mass of the companion, which we don't see. It's the mass of the pulsar, the mass of the companion again, and the sine of the inclination angle. For this, the observation gave 1 solar radius. So this gives you an idea about the size of the thing. Yeah? Well, m2 over m1 plus m2, this wouldn't be 10 to the 5 or 10 to the 6. Yeah? It would be something like 1 or maybe 10, but not much different from 1. So this is approximately 1. This is bounded by 1. So this is, gives you the order of magnitude of the semi-major axis. It's about a solar radius, maybe 10 solar radii, but not more than that. So this is, as I said, the system is very close. But the distance is still big in comparison to the Schwarzschild radii you expect. Because from this number, you can estimate the masses. Again, the sign of I is limited by 1. And this mass ratio, m2 over m1 plus m2, is 10 at the most. And then you have just one factor of m2. Yeah, you have one factor of m2 and then a rest which is not very much different from 1. So you see the order of magnitude of the mass must be something like a solar mass. Maybe 10 solar masses, but would be possible according to this analysis, but not very much different from a solar mass. And this means these are objects which are stars, which are orbiting each other very closely with an orbit of 7 hours. And so they should produce gravitational waves. So the gravitational waves should be observable. The decay of the period should be observable. This I said this analysis, a simple analysis, which gives this 4 orbital elements, is based on a Newtonian theory. That you consider the motion, as we did until now, that these are just mass points obeying Newtonian laws of motion. You can do a first post-Newtonian correction. Yeah, you take relativity into account for the motion of the two things, but not with the exact equations. Nobody can solve the exact two-body problem with a full relativity theory, but you can do it to a certain approximation, where you develop in powers of 1 over c squared, and you take only the leading order. That's what is called the first post-Newtonian approximation. This has been done in the late 70s, early 80s for this system. I will not talk about this. I'm sorry, it's too complicated for me. The post-Newtonian expansion for such a binary is really, it's a very, very complicated thing. I had thought about if I could produce this here, but it would take me, I think it would take me 2 weeks. Yeah? So if I want to present it fully, then it would take me 2 weeks. So I will not do this. I'll give you references where you can find this if you're interested in details. So what came out of such a post-Newtonian analysis, going beyond the Newtonian theory, is that you can deduce the masses individually and the semi-major axis. For the masses, you get 1.44 solar mass. This is M1 is a pulsar, which we observe. So that's a very typical value for a neutron star. So typically, they lie between 1 and 2 solar masses. And for the companion, one gets 1.39 solar masses, which would also agree with a neutron star. It would approximately also be possible for a white dwarf. It's about the so-called Chandrasekhar mass, which gives the limiting mass for a white dwarf. So in the beginning, it was not quite clear if the companion is a white dwarf or a neutron star. Could be both. Now we are fairly sure it's a neutron star. It's a dead neutron star, which doesn't do anything. It's just sitting there, well, moving around with the other one. I'm sorry?
How do we know this?
Yeah, what will... Well, the mass is one indication, and there are other observations. Let me think. So I think a white dwarf is now more or less ruled out. I've forgotten what the other information were, but I can check again. I can tell you next time. So I think nowadays people are more or less convinced that it is a neutron star. And we now know also the semi-major axis. It's 2.8 solar radii. So that's 1.5 solar diameter. So the whole system does not fit into the sun, but it's not bigger, not much bigger than the sun. Yeah? And you have 2 stars inside the system, each of which with more than a solar mass. So it's and this goes around in 7 hours around each other. So it's a very powerful, very powerful system in comparison to all other binaries we know, ordinary binaries. And from this post-Newtonian analysis, where relativity is taken into account, you also can calculate the so-called periastron shift. Yeah, that's what, in the case of the planets, you call the perihelion shift. Now you call it the periastron shift. It's the closest point to the other star. Astron, what is it? Astrum, or what in Latin? What is the word for star? I think, or is it Greek?
I think it's Greek.
It's Greek. Astron. Astron is a star in Greek? Okay, anyway. So this has something to do with star. Yeah? And Helios, of course, has something to do with the sun. So the perihelion is a point closest to the sun. The periastron is a point closest to the companion star. And the, and the shift by which this perihelion precesses is 4.2 degrees per year. You might say, oh my God, that's really big. For comparison, remember the perihelion shift of Mercury is 43 arcseconds per century. Yeah? 42 degrees per year. So this is, you would say, oh, that's a highly relativistic system. Yeah? The perihelion shift is big. But if you refer it not to a year or a century, but if you rather refer to a period of the system, then you see that the two things are not so much different. Actually, 4.2 degrees per year means 1.7 arcseconds per period. The period is only 7 hours. Yeah? And if you do the same calculation for Mercury, you find that it is 0.1 arcseconds per period. The period is 88 days for Mercury. Yeah? So you see, this is not very much different. So this is totally non-relativistic. Yeah, it's a tiny effect. Nobody would say that the motion of Mercury is highly relativistic. And you see, okay, this is bigger by a factor of 10 or so, but not much bigger. So it's still not very highly relativistic, in spite of this somewhat misleading observation that the perihelion shift is 4.2 degrees per year. And if you now know all the orbital elements, you can calculate this. Well, we did the calculation only for a circular system. Yeah, the formula I derived was only for a circular system, but the but the order of magnitude is not very much influenced by the eccentricity. So you can calculate just the order of magnitude of this in-spiral time with the formulas I've given you last time, and you find something like 300 million years. Yeah? So you have to wait for 300 million years until the two things really merge. This gives you a good idea about the order of magnitude, although this idea of Newtonian point masses, of course, has to be abandoned at some point. So if some of you will be around in 300 million years, then you would see a marvelous gravitational wave signal coming from this system, yeah, when these two things merge. So the eccentricity, just I'm not quite sure, did I say this? I've shown it to you on the view graph. The eccentricity is 0.6. Yeah? And if you feed this into the formula for the radiated power, you see that the influence which comes from epsilon is not very big. It's in the order of 1. It's doesn't change the order of magnitude. So if you just want to calculate the order of magnitude, you can do it with a formula for circular orbits. So here's a picture of the system. Here's the sun for the sake of comparison. And this is this binary pulsar. So you see it's a little bit bigger. Yeah, the system is a little bit bigger than the sun, but not much. Actually, we have found more binary pulsars by now. In particular, we have found one real double pulsar, where both objects are pulsars. This is now the best object for testing general relativity we have. And this system fits into the sun. Yeah, this is so small that it totally fits into the sun. And here's another one, another famous example, where you have almost circular orbits. Obviously, one mass is much bigger than the other one. So one of the two masses rotates about the center of mass in a very small circle, and the other one in a much bigger circle. And again, the system is only slightly bigger than the sun. So that's a typical size of these binary pulsars, which are used for testing general relativity. We have a couple of them by now. Well, and now we can test our formula for the decay of the orbital period. So what is plotted here on the vertical axis is essentially this d capital T by d little t, which I've shown you in the beginning. And well, here it's plotted in a slightly different way. What is plotted is the shift of the periastron after one revolution. But this contains the same information as as a time derivative of the period. So this line, this continuous line, comes from the calculation. We know the orbital elements, so we can calculate, according to the formulas we have derived, the way in which the period changes. And these are the observations. We can also observe how the period changes. There's a period with a redshift observation. The period can be determined with high accuracy, and you see how it changes. This was, I think the most important theoretical paper on the Hals-Taylor pulsar. It was by Taylor and Weisberg, Joel Weisberg, a theoretician, published in '82. And there you see already that it fairly well follows the suggestion which comes from Einstein's quadrupole formula. So this was from observations already at this time a fairly convincing confirmation of the quadrupole formula. At this time, the Nobel Committee was still skeptical, so they did not give the Nobel Prize shortly after '82. They waited for another 10 years. They waited for more observations. Well, this is the situation from the year 2005, and now you see how excellent the agreement with the theoretical prediction is. And I emphasize this is not a fit. This is really important. Yeah? You calculate the curve from the orbital elements, and there's no free parameter. Yeah? You calculate the curve, the precise curve from the theory after you have determined the orbital elements. And then you make the observations. And the observations fit perfectly to this observation, to this theoretical prediction. Here you see no error bars. Why not? Because they are so small that you cannot see them. So the points really are precisely on the curve. And well, here in '93, the Nobel Committee was of the opinion, now the agreement is good enough, now we could give the Nobel Prize to these guys.
Is there any evaluation parameter which quantifies the error?
The question was if there is a parameter which quantifies the error. Actually, well, what I said was that the error bars are too small so that you cannot see them in these diagrams. But of course you can estimate them. Yeah? So you could say, I don't know, to what sigma this would fit the curve. But I have to admit I don't know the number. But one probably can find out. But just from looking at this diagram, I think it's fairly clear that this is a marvelous confirmation of the theoretical prediction. And as I said, Einstein's quadrupole formula was a matter of debate for many, many years. Yeah? Many people said, oh, the derivation is somewhat dodgy. Yeah? We do not really trust this formula. But if something is confirmed by observation in such a marvelous way, then there's practically no other possibility than to accept it. So yeah, Einstein was right again. He's always right. It's really amazing. Okay, so I said already that by now we have some other candidates. In particular, we have this so-called double pulsar, where we saw two pulsars orbiting each other. So this is a case where both companions emit radiation, and so this was for a couple of years. The best candidate for testing general relativity. So it improved the accuracy even further. But this system in the beginning had a problem because there were eclipses. Yeah? In the case of the Hals-Taylor pulsar, there are no eclipses. We see this shining object always. It's never eclipsed by the companion. But here we saw eclipses. So one of the pulsar was gone for a certain period, then it came up again, then it was gone again. And this came kind of irregularly. So people were really worried what was going on here. And then in this paper, the explanation was given. One of the companions is associated with a magnetosphere, yeah, a magnetic field which surrounds this this object in a kind of a toroidal shape. And yeah, this magnetosphere is rotating with the pulsar. Yeah, so we have this donut. You have to assume that this donut rotates around an axis which is not the symmetry axis of the donut. Yeah, so then it makes a fairly complicated oscillating motion. And this gives the impression that when the other object moves behind this magnetosphere, that it is eclipsed in a way which it seems at first sight irregular. Yeah, because this wobbling motion has not an obvious period. So that was the explanation for these funny eclipses. And after this has been clarified, the system was well understood. It was studied for a certain while. Then, unfortunately, one of the pulsars could no longer be seen because, the orbital elements change in the course of time, and this means that if this lighthouse, which is emitted from this lighthouse radiation, which is emitted from a pulsar, has hit us for over a certain time, now the orbital elements change, and then the cone does not longer meet us. Yeah, so it's still there. We are sure it's still there, but it doesn't meet us. So we cannot see this object anymore. Okay, so and as I said, we have a couple of other binary pulsars. They are intensively studied. Our colleagues in Bonn are at the forefront of this. There's a Max Planck Institute for Radio Astronomy, Michael Kramer, Norbert Wex, these people. So they are among the leading experts who are investigating these binary pulsars and testing general relativity with them. So I think it's fair to say that this is the best test of general relativity we have today. Yeah, the best test comes from the study of binary pulsars. You could also test alternative theories, and actually some alternative theories have been excluded with the help of this theory. Maybe you have heard about MOND, modified Newtonian dynamics. MOND is doing very badly with respect to these observations. They try to really stretch the theory so that it's still able to explain the observation, but it's difficult for MOND. And for other theories also. So also other theories have been at least strongly restricted by these observations. Whereas Einstein's theory sits smack in the middle of all observations. Yeah? It fits all of them perfectly well. Okay, so this was this chapter on the binary pulsars, which I have given in a different way than most parts of this course. But now I go back to chalk and talk for a while. So I think I just pull this out. Okay, and I come to the next chapter. I don't know if this switches off automatically. It switches on automatically, so I guess it will also switch off automatically. Okay, let's just wait a few seconds. And then I'll continue with a new chapter. Will be chapter 4, gravitational wave detectors. So I have mentioned already briefly how gravitational wave detectors operate, but I will study this now in some more detail. And as you probably know, and as I have mentioned already, there are two types of gravitational wave detectors which have been developed in the course of history. Oh, I think it's switching off. These are the first ones which were developed. These were these resonant bar detectors. And I've thought for some time if I should talk about resonant bar detectors here, because they are kind of outdated now. Yeah, we have. Okay, so I was just saying that. I considered for some time the question if I should talk about resonant bar detectors at all, because now, since the other type of detectors, interferometric detectors, have found a signal, of course, everybody speaks about the interferometric detectors, and almost nobody speaks about the other class anymore. But actually, I think for understanding the idea of what a gravitational wave is and what it does to certain detectors, I think it is helpful to understand what a resonant bar detector is. And in history, they played an important role for quite some time. So I thought I leave this section. So I begin with resonant bar detectors. I will then again show you a couple of pictures of them. So right now, I think there's only one of them in operation, and that's a small one in Brazil. But I wouldn't exclude completely the possibility that they become more fashionable again in the future, because they might complement the observations from interferometric detectors in a certain way. So they were invented. This idea of using this kind of detector was invented by Joe Weber around 1960. Weber was actually, he had an engineering background. He was in Princeton. He came into contact with John Wheeler, the famous relativist, and he talked to him about the possibility if gravitational waves could be detected with the help of big masses, metal cylinders, maybe 1.50 meters in length and maybe 1 meter in diameter, or a little bit less. And the idea was that when a gravitational wave came, and if it had the right frequency so that it could produce a resonant wave, then it might be possible to just to observe the deformation of the thing. So the typical way how this looks like, if you look at it from the side, then it would be this kind of cylinder, and if from here comes a gravitational wave, then it would be rhythmically deformed into this way, then back into the original shape, and so on. And of course, the question is, can you really measure the change in can you really measure the deformation? And what Weber did it with the help of piezo crystals. Yeah, so he glued piezo crystals onto the thing, and now if it is deformed, then it should be possible to observe this. He did this for many, many years. I met Joe Weber only once. This was in 1980 at a conference. And at this time, he was still very active. So he had several of these detectors in operation in the United States, and he was still very active trying to observe gravitational waves. He died, I don't know, around 2000 or so, and everybody is convinced that he never found a signal. Everybody, with the exception of himself. So he claimed that once he had found a signal, but nobody else believed that this was really true, because the general idea was that the general impression was that the amplitudes are too small to be observed with this kind of instrument. What I want to do here is to tell you the basic idea of how such a thing would operate, but not just in terms of a picture, really in terms of formulas. Yeah? So I want really to derive formulas, what kind of amplitude we can expect from an incoming gravitational wave if we are in the resonant state. And I will do this calculation not for such a big solid object of a cylindrical shape, but for a simplified object where we have just two masses connected by a spring. Yeah? So this is sufficient for deriving the formulas which describes the basic idea. But of course, it's much simpler than working with an extended solid body. Actually, in his first paper from 1960, Weber discusses this simple example in some detail. Yeah? Two masses connected by a spring. And it's also discussed in the book by Miesner, Thorne, and Wheeler. Yeah, this big relativity textbook from 1973. They discuss this simple system in some detail. And what I do here is largely patterned about the presentation in these two sources. So in order to do this, we first have to recall that how freely falling particles behave in a gravitational wave. We have derived this, I don't know, 6 weeks ago or so, when we discussed the plus mode and the cross mode of gravitational waves. So freely falling particles, the equation for this will be the starting point, and then we introduce external driving forces. Of course, if you have a solid body, then the individual atoms or molecules are of course not freely falling. Yeah? They are connected by intermolecular or interatomic forces. Also, I am not. My constituents are not freely falling, fortunately. Yeah, so they are connected by intermolecular forces. And if a gravitational wave hits me, then if it hits the resonant frequency of such a connection, then these particles of which I'm built, they would start oscillating, right? So in this way, I could work as a gravitational wave detector. So and how this is to be described quantitatively, this will be the plan for the next 60 minutes or so. So for that, we need to start with the equation for the freely falling particles. And actually we did this in worksheet 2. So in the lectures, I had introduced a quantity which I called yk. We started with coordinates which were called xk. They were tied to the particles. So if the particles moved, then the xk coordinates moved with them. So in terms of the xk, we didn't see any motion. You remember this? Yeah. And then we changed to new coordinates, which I called yk. Yk really measures the distance from a central particle. So if the yk changed, this really gives us the change of the distance. And we derived the formulas for the yk as a function of time in the lecture. This gave us the plus mode and the cross mode. And in the worksheet, we derived a differential equation which involves the curvature tensor. And that's what I want to use now. So we had, for the yk, we had a second order differential equation. It was a linear differential equation because we linearized it. Yeah? So the formula is supposed to be true only as long as the YL are small. Yeah? So we have so we have here your YL. You have here the time t. You have here your central particle, the 0 in this coordinate system, and then you have here this oscillating coordinate yk. And the formulas we derived were valid as long as everything can be linearized with respect to the y's. So this is true as long as this neighboring particle is close to the central particle. And the coefficient in front of this was determined by the curvature tensor. This was the differential equation. The curvature tensor taken at time, ct, and at the position 0, at the central particle, yl. This was a differential equation. Second order differential equation, obviously the solution to this is some kind of oscillator behavior, right? And then we related the curvature, again in the worksheet, the curvature tensor to the amplitude of our wave. So there was a factor 1/2 of it. So RK0L0 was 1/2. And then the second derivative with respect to x0, which is c times t of the gamma KL. Again, I should write arguments because this holds only, K0L0, this holds only at the origin, where now this gamma KL is a plane harmonic wave. So it's something of this kind, AKL exponential I shouldn't use the index K because I need, I is the imaginary unit, say I K sigma X sigma, okay? So that's what we had, I don't know, 5 weeks ago or so. And we want now to, this is for freely falling particles. Yeah, it's for freely falling particles. You put the particle into a certain position and then you let it go. And under the influence of the gravitational wave, it will start oscillating. And what we now want to do, we want to modify this differential equation by a fourth term. But first, let me write it out explicitly. So of course I can calculate the second derivative for this form of the, and do I do it only for a plus mode? Let me check. No, for the time being I leave it. For the time being I leave it. Yeah. So with an with an external force, so if I let the particle not freely fall, if I have a force acting on the particle, then I have to modify this by adding a term. Then my differential equation will become this here. What we had already. 0 YL plus a force. Well, this is an acceleration, right? This is an acceleration. So if my test particle, which I place here, has a mass m, then I have to divide the force by the mass to get the acceleration. And this is the equation we now want to work out further. And I want to do this, as I said already, for the case that this mass is one of two masses connected by a spring. And this force is then provided by the spring. So let me draw a picture for two masses. And for simplicity, I'm assume that both of them have the same mass. So let me first draw a picture, and then let me specify this force. So I have 3 axes. I'm now in the y-coordinate system, yeah? y1, y2. Or do I do this in the x system? Wait a minute, actually I could. Yes, I could do it in the x system, because then the particles move, yeah? I want to have them move, yeah? In the y system, they would when they were freely falling, they would just stay where they are. But in the x system, of course, they are moving. So the idea is that I have my gravitational wave coming in this direction. Yeah? So I choose my coordinate system in such a way that the gravitational wave moves in the, in the 3 direction. And now I put my system, consisting of two masses at a spring, into the way of this gravitational wave. Of course, I don't know from where the gravitational wave comes, so I have to take into account the possibility that my spring makes any angle with respect to the chosen axis. So my spring is here. So I have here one mass. I have here the other mass. And they are connected by a spring. How to draw a spring? Maybe this way. Yeah? And now the wave comes in, moves these two masses. So this gives us a force, so to speak, in quotation marks, which would act onto these masses if they were freely falling. But then we have this force coming from the spring. So the total force acting is this here. And this makes the masses move. And in general, we will have an axis, an angle theta here. And we have an angle phi here. Yeah? So, of course, we cannot assume that our spring is associated with, is adapted to the chosen coordinate system. And for this system, we want now to first to write down the equation of motion in full detail, and then we want to solve it. And this will tell us, we will get oscillating solutions. And we will see how the resonance frequency is related to the parameters of the wave. So my differential equation is now what? It is d2 yk. This has only one index. This is nonsense here. dt squared is, and for r we have this here. It's a second 1/2 second derivative with respect to 0. Gamma KL at CT and 0 plus, let me write this as it is for the time being. I insert this a minute later. Let me first calculate this term here. So this is 1/2. Okay, I have to differentiate this here. I have to differentiate this twice with respect to x naught, which is c squared times, is the c squared correct? Let me check. Sorry, I forgot the c squared in the differential equation. I remember that when we did the exercise, we also had problems with the c squared. I think the c squared is here. So it's a derivative with respect to x naught squared, sorry. And then I have, no, here I have a c squared. Oops. Here I have a c squared. Yeah, these factors of c, they are really driving me crazy. But, by law, I have to, I have to take them into account. Okay, and now I get a 1/c squared. I hope that's correct. Is it true that now the c square factors are gone? Yes, I think so. I think so. And now I differentiate with respect to t, and this gives the real part. I differentiate twice. This gives, or I can write it in this way. I do it without the c squared. I really differentiate with respect to x naught. Then I get a k naught. Yeah, I get a k naught twice. I get minus k naught squared akl e to the I k sigma x sigma. And I have to evaluate this at ct0 plus fl upper L over m. Ah yeah, now it becomes nice. The minus sign can be written in front of everything, c squared. And k naught squared is omega squared over c squared. Yeah, k naught squared is omega squared over c squared. And then I have the real part, akl. And here I have to insert ct. So I get e to the I k0 ct and plus 0 plus 0 plus 0, and that's it. So k0 with a lower index was plus omega, right? Plus omega over c. Let me check. Boop, 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 boop. According to my notes, it's minus omega. Okay, I believe my notes. Then I have minus 1/2. These factors cancel. Omega squared. That's omega of the gravitational wave. So remember, when we associate this with the source has a period capital omega. The little omega is 2 times capital omega. Yeah? Gravitational wave only comes with twice the period of the source. There's an index L missing. AKL, and this K0 times C is minus omega, according to my notes. Hope it's consistent with what we have done earlier. And that's it. Well, actually, I will specify this now for a plus mode. For the plus mode, I have AKL, and it moves in the z direction. Yeah? So the amplitudes are in the xy direction then. So here I have zeros, and here I have an amplitude a plus, minus a plus, 0, 0, right? So this gives me, I've always forgotten the YL, the Y, oh my goodness, what a nonsense. Okay, here it is correct. See, index K, index L, that's correct. Here index K, here I forgot the YL. Index K, index L, here's the YL. Everywhere. Okay, so I have d2 yk by dt squared is minus 1/2 omega squared. And okay, I have only one mode, So I don't have to care about the phase factor. I can choose my initial time t equals 0 in such a way that A plus is real, right? In general, if I have two modes, the plus mode and the cross mode, they will not be in phase. And I have to take into account that this has to be written as A plus modulus times e to the I phi, yeah, to a phase. But if I have only one mode, I can choose my initial time in such a way that A plus is real. So this would be, how do I write this now? I write this in matrix, maybe this way. So I have now A plus minus A plus 0 times y1, y2, y3. I forgot this term. The real part of this is just cosine omega t plus FL of n. Yeah, this is now also a 3-column, right? Okay, so we have to discuss the FL. What is the FL? And yeah, the FL is, I think I make another picture. I cannot squeeze this into this picture. Let me draw the, oops, this diagram again. So here I have my x3 axis. Here I have my spring. Okay, so this here, this is my YL, right? This is my YL, which depends on t. Yeah, the thing becomes oscillating. Yeah, we have here the second time derivative. This thing becomes oscillating if the gravitational wave acts. So this is, yeah, something in the rest position. Yeah, if the spring is there's no tension in the spring. So if YL of t is equal to SL and I don't impose an initial velocity, then the thing would stay as it is. Yeah, and then a rest, and this gives the elongation from the rest. So my force is then FL. The force is then well, minus a certain spring constant k. We assume that the spring is a linear spring. Yeah, psi L of t. And we take a damping into account. How do I call the damping constant? Gamma? Yes, gamma. Which is proportional to the derivative, to the velocity, right? So positive gamma means that yeah, the force wants to make the particle slower, so it's really a damping, right? Positive gamma means damping. So this is a, how do we call this in English? Restoring force? Or so in German I would say rücktreibende Kraft. What's the English for that? Is it restoring force? Yeah? Okay. And this is a damping. Okay, and now I can collect everything together, and then I have the differential equation, which I have to solve. I should have said we don't want to allow these masses to move out of this line. Yeah? So we think that the spring is rigid in the sense that the masses can move only along this line. Yeah, they cannot swing around in this way. Then I can make this into a scalar equation. Then I could write that YL of t written as a 3-column vector is a scalar S plus a scalar, or I write it separately. I think that's better. I write the SL as a scalar S times, well, how did I call the angles? I called them theta and phi as usual. So this would be cosine phi, sine theta, sine phi, sine theta, cosine theta. Okay? So these would be the 3 components of the SL. And The psi L, similarly, is a scalar factor psi of t times the same direction vector. Okay, now I can come back to my differential equation. So on the left-hand side, I have the second derivative with respect to t of y. Y is this here. Second derivative of this. Okay, I do it slowly. S plus, I think I can do this in one step. So I have to take the second derivative of this with respect to t. Second derivative of this is 0. Second derivative of this is this here times this direction vector, which is time independent. Yeah? Cosine phi, sine theta, sine phi, sine theta, cosine theta. This is what? Then I have 1/2 omega squared, a plus, a minus, and zeros everywhere else. Acting on y. Y is this here. So this is s plus psi of t times this direction vector. That's nonsense. There's a minus in front and the thing is still called a plus. Actually, I could call it just a because I have only one amplitude now, but it is a plus mode, so let's stick with this terminology. And then I have cosine omega t, shouldn't forget this. Cosine omega t plus fl divided by m. Plus fl divided by m means, let me continue here, minus k over m psi l. Psi l is psi of t, and then again the direction vector, cosine phi, sine phi, sine theta here, of course, cosine theta, and this divided by m, minus gamma over m, and now the first derivative, this is d psi by dt, and the direction vector, which is constant. So you see that almost all terms are proportional to this direction vector. The only one which is not of this type is this here. So I take all the other ones together. Then I have second derivative. There's this here. And I have this term here. This is with minus on the right-hand side, so it becomes plus on the left-hand side. And this becomes again plus on the left-hand side. And everything is to be multiplied with this direction vector. And on the other side, I have only this term here. So this is omega squared half s plus psi of t. And then I have to multiply this out. Well, every terms contain a factor a plus. And then I get in the first component this with a plus. In the second component this with a minus, minus sine phi, sine theta, and in the last one a 0. And the cosine omega t. Okay, so you see we get a scalar differential equation for psi of t. In order to get rid of these inconvenient direction vectors, I multiply everything in the sense of the scalar product with this vector. So I multiply everything with cosine phi, sine theta, minus sine phi, sine theta, cosine theta. then this gives just the 1 because this is a unit vector, right? So I have d2 second derivative with respect to t of psi plus k over m psi of t plus gamma over m d psi of t dt d psi by dt plus 1. Yeah? This times this vector, no, with a plus sign, sorry, with a plus sign. Yeah? So this is a unit vector. I multiply it with itself, so I get a 1. But on the other side, I get something different. Half s plus psi of t, a plus, cosine omega t. Maybe I should put a bracket here. So this is what? This is cosine squared minus sine squared. Times sine theta. Okay, and that's it. Yes. Let me see.
I think the square is missing.
Where's the square missing? You're right. Thank you. Thank you. There's a square. Let me check if I got this right. Oops. Where is it worked out? Oh yes, yeah. I was confused for a while because I had here a linear term in psi which puzzled me. But well, we assume that the elongation is small, right? So we have our spring, which has a certain state where the masses are at rest, and now I elongate them. But I elongate them only by a little, by a little amount. So I assume that this here can be approximated by the S. Yeah? So that the length of the spring in the relaxed state, that this is much bigger than the elongation which is produced by the gravitational wave. So then, well, indirectly this was already used by assuming this law. This is Hooke's law, right? That the force is proportional to the elongation from the rest. And of course, if you elongate the spring by a very big amount, then this is no longer true. Yeah? This is also only an approximative assumption, which is true for small elongation. Hooke's law is not a general law of nature like Newton's second law or so. It is just an approximative assumption which may be assumed if we have oscillating things with small oscillations. So in agreement with that, we assume that here the psi of t can be ignored. And then we have a nice differential equation. Let me rewrite it in a way that everything which involves the psi is on one side, and everything which does not involve the psi is on the other side. And how much time do I have? Let me check. Come on. 1 minute. Okay, it's just enough to write it down. And then we will solve this differential equation next time. I think that's all I need. So our differential equation is the following. Second derivative of the elongation of psi with respect to t, of course. So then I order them with respect to the degree of the derivative. So the next term is then gamma over m times the first derivative plus k over m psi of t. So you see that's the left-hand side of a damped harmonic oscillator equation, right? And we have a driving force on the right-hand side. If I neglect this psi, then it is just given by a plus omega squared half. Cosine squared minus sine squared can be written as cosine of 2 phi, right? It's a little bit shorter. Sine square of theta times cosine omega t. So we have a periodic driving force, and this is driving our damped harmonic oscillator. And we will next time derive the resonance condition and then see for what kind of frequencies we could expect a nice resonance signal. Okay, have a nice weekend and see you next Monday.